okay? So cellular communication, they were able to send this data back to some server, and then they could take a look at how many times the doors would open and close. And that information told them how many times people were getting on the elevator. Make sense? Right? So before, they were sending out a truck to service all the elevators in the city, or for that matter, in their territory. They were sending them out once a month. And this was an opportunity for them to right-size that fleet and to save some dollars. That same customer, okay, again fictitious, is now in their second generation of product. And now what they want to do is, just like what you see on your tables, on the edge. They want to control what actually happens at that account. They want to understand and do some preventive maintenance. They want to understand what's going on with that particular customer. And so they're able to measure vibration, they're able to measure sound, they're able to measure humidity and temperature and other things that they never measured before. And these are learning machines. They can take that information and they can do some preventive maintenance or predictive maintenance on the products. In fact, you never know what you don't know, and so there's an opportunity here for a learning machine that goes into the elevators. So now I think to myself, what will be the next generation of the elevator, right? I'm thinking to myself, the elevator is going to have a personality. You're going to walk into the elevator. How many people remember those guys on the elevator who would take you to every floor and tell you what's on every floor? Yeah, so imagine you walk into an elevator, there's no buttons. There's just a display. And the person says, well, hello, Mr. Smith. Haven't seen you since Thursday, right? Because it knows who you are. And it might have a discussion with you. It might tell you that there's a new chef in the kitchen downstairs at the restaurant. It may tell you a lot of other things, and it may ask you questions. This is another source of income for elevator companies, okay? This is just my idea of what this company would do. But if you think about it, think about what your design would do. How many people in this room have done an IoT design? And how many have never done an IoT design? I know there's a lot of people over here, right? Never done an IoT design, great. So what we're going to do is we're going to talk about some of the things that you need to know in order to get the job done properly. And that's what these brilliant people are going to tell us all about. Okay? So just so that you know, some of the things to think about is, I think I lost my picture here. We're going to follow the money. So the money it's all about what is the investment all about? These things are pretty pricey. I don't know if anybody's done, well, for the people who have done IoT designs, how many people was over $1 million? Yeah. So there's a lot to an IoT design, especially the first one. Design for manufacture, these are all things that you need to know. And then I have experts here that are going to talk about these components right here. So focus on your core competency. What is it that your company does? It makes widgets, right? You may not be an expert in RF. You may not be an expert in power, okay? These deployments may go somewhere where you have to have some kind of special power. Firmware, you may not be an expert in this area. I'm sure you have some of these core competencies, but you may not have them all. How many in this room are consultants for this industry? Either an IoT consultant, or hosting, or a CM, or all these different disciplines. There's a lot of consultants in this room. And in fact, almost all these consultants in Northern Ohio, I know them all. And so this is what we're here for. We're here to say, this is the infrastructure that we have in Northern Ohio. Let's take advantage of it. Moving along, some of the important items. There's, for companies that are startups, and I've worked with a lot of these companies, okay? A lot of companies come in and they don't really know what they don't know yet. Take advantage, learn from the experience of others, okay? Give me a call. Hosting versus outsourcing. A lot of people think, well, I have to host everything. Make sure you really do the pricing on that, because if you're hosting everything, your security has to be at a certain level, etc. And then as far as finding solutions, there's example code out there already, there's development boards. There are a number of premier consultants here. 3 of the 4 people on this team here are consultants, in fact. And then, partner with your stakeholders. Understand what your customers really need from your products and interview your customers. This is very important. Now I'm going to introduce the panel. So I'll start off with Glenn Amelko. Glenn is going to talk a little bit about RF. Glenn is with a company called Aclara, or Hubble, as it's now called. And they have the oldest, I believe, IoT design in the territory. They do wireless meter reading. Okay, so many of you may remember a company called East Ohio Gas Company. John Halston is with Halston, or is the president of Halston & Associates, and he's been doing consulting work for years and years. In fact, I believe you have more than a gazillion parts out there, and there are products out there in the field, am I right? What is the real number?
It's in the thousands.
It's in the thousands? And then James Ray, Vice President, Nottingham Spur, also a consultant for IoT. And then Joe Tennant, Vice President of IT Services over at Seven Signal. So what we're going to do is we're just going to kind of go through some of their technology. There was a 5th panelist who did not make it today. That's my friend Galen Fisher, who was going to talk a little bit about security. When we get to the security piece, that's going to be broken up between Glenn and Joe, and so that we can go through that. So let's start with RF.
Hi, Glenn. Test 1. Okay, takes a second for the mics to come on, everybody. Notice that before I forgot. Thanks, Mike, for having us here, and thank you, students. It's really great to see that many young, creative minds here. And thanks, John, for introducing us. That was great. As John mentioned, my background is in RF and communication and a whole bunch of other things. I've been around the industry. I think you said I was the oldest. No. Oh, you said I had the oldest. Oh, that's right. I've been personally responsible for the deployment of over 15 million internet-connected devices. So it's just a few. Those are primarily utility monitoring systems, water, gas, and electric, mostly to read your bills, but we've been doing all kinds of other things with them. Just advice in terms of communication systems. Rolling your own is really, really hard. There are lots of pitfalls, and there are so many things that you can get today that are off the shelf. Arrow can provide them, and the other manufacturers, reps in the area, as well as you could go directly to places like, I'm sure people have heard of Arduinos and other such devices. Many of those things are already prepackaged. You'll see technologies behind me, and I don't even need to look at the slide. Anything from RFID, which is very low power and 0 power, to Bluetooth and Zigbee. I'm sure people have heard of those things. And the selection of the technology that you use, whether it's that end of the scale or cellular or even satellite communications and beyond, has a lot to do with the range of operation you're talking about. If I have a personal device like a Fitbit on, the range of communication for that is between that and my phone. So I'm going to choose a low power technology so that this thing doesn't need recharged every 2 hours. And I'm going to use a low power communication system, something that can move the data that I want over the range that I need to move it over. So you have to consider What is that range? Also, you have to consider the volume of the data. If I need to move lots and lots and lots of data, I might need a wider bandwidth communication system that's going to require more power, and more range, and better antenna systems. And so, that choice might mean that, for example, Wi-Fi or something like that makes more sense than something that's very low power and very limited bandwidth. So you have all of these trade-offs, and I've listed a whole bunch of them up there, and I'm not going to read the slide to you. I'm sure you can all read. Those trade-offs result in technology choices, and consultants in this industry, I'm sure that the guys here and anybody in the audience can help you make those decisions and decide what is the best technology that you should use for the communication system that you need. The other thing to consider is, I've had this discussion recently with a lot of people in our industry. We talk about edge compute, and we also talk about moving gobs of data up to the cloud to do this, big data analytics, as everybody calls it, or coins the term these days. And the question is, where do you want to do your work? And there are trade-offs. One of the trade-offs is, if you do all the computing at the edge and you return a yes-no decision up to the cloud, you lose all of the information that you had to make that decision. So if you suddenly find that your device at the edge of the cloud is making bad decisions, you don't have visibility into the data that it was using to make those decisions. So redesigning or changing that algorithm becomes fairly difficult. On the other hand, if you move everything to the cloud, well, let me give you an example. What I'm telling you right now, certainly I saw there's a video recording going on. You can record this conversation or this discussion or lecture or whatever you want to call it that I'm having with you. That would be megabits, if not gigabits, of data. You could certainly just do an audio recording, and that would reduce that data down to kilobits, and that would be reasonable. Or you could simply take the information content of what I'm telling you, and maybe that's only a few bits. Maybe most of you already know what I'm saying. So, and now you could say, I'm just going to move the information content through the communication network. I still then get that information content if I've done my job right in the cloud. I can still do a post-analysis or go back and change algorithms. But if I just simply say, did Glenn talk? Well, you got a yes, no, you got 1 bit worth of data, you got nothing out of what I said. So you need to think about how much data you need to move, whether you really need to move it all in the video analogy. Do you need to move all of that data, or do you just need to get the key salient information out of those sensors and move that up to the cloud for processing or either now or post-processing later? So, a little bit long-winded, but these are all the considerations. What's the latency? How much data do you need to move? How quickly do you need to move it? In the elevator example, we probably don't need to move the information every time somebody steps in or out of the elevator, at least not for that content. You do need to know that somebody went in. On the other hand, when somebody walks into that elevator and you want the elevator to greet them properly and say, hey John, how are you doing today? Then you might need to move a lot of data, and you need to move it quickly. Or you need to have some of that information stored locally so that you can access it quickly and regurgitate it on the spot. So there's a lot of trade-offs here, the RF band that you use, the communication system that you're using, that'll dictate the size. Lower frequency transmitters require longer antennas, and higher frequency transmitters require smaller antennas, or only have to have a smaller antenna, but they have limited range. So that's a lot of stuff to try to dump in 5 minutes, and I probably went a little over time, but I'm going to turn it back to John.
It's quite all right. By the way, I do have a demo of this elevator. In case you're ever interested. Time for firmware.
Yeah, firmware, I want to first thank Mike for putting on this great event, and I'm sure the team of other individuals helped them out. And thanks, John, for the invite to the panel. I really appreciate that. I was asked to talk about firmware. I call it the unsung hero of technology. I'm trying to prove that point here in today's talk. So let's talk about something that quietly powers the Internet of Things, firmware. While the term might sound dry, firmware is the brain behind every smart device, from your smartwatch to industrial sensors to John's IoT-enabled elevator. Specifically for the few minutes we have today, we'll look at firmware's important role in IoT. What is IoT firmware? Firmware is the low-level software embedded in IoT hardware and is essentially the operating code stored inside a device. It's stored in non-volatile memory like flash and acts like an interface between the device's hardware and higher-level applications or network communications. Unlike regular software, it is designed to interact directly with sensors, chips, and communication modules. For example, in a smart thermostat, the firmware controls the temperature sensor, the Wi-Fi module, and how the device responds to user input. Why is firmware so important in IoT? Well, firmware defines the capabilities of an IoT device. Think of firmware as the instruction manual for the hardware. It determines how the device collects data, communicates with other systems, and responds to commands. Without good firmware, even the most advanced hardware is useless. It also affects battery life, security, and overall performance. Firmware development and IoT challenges. Developing firmware for IoT is tricky. You are often working with limited memory, constrained power, processing power, and real-time requirements. You also have to consider over-the-air updates which allow devices to be updated remotely, critical for patching security vulnerabilities. A single bug or exploit in a firmware can put thousands of devices or even millions of devices at risk. IoT security in the future. IoT security is a massive concern. Firmware can be an easy target for attackers because it's often very neglected, especially after a product is shipped. That's why secure boot, encryption, and regular field updates are becoming standard. As IoT evolves, we'll see smarter firmware capable of self-healing, AI-based decisions, and more autonomous behavior. So in short, firmware is the unsung hero of the IoT ecosystem. It's the hidden layer that keeps our devices functioning, secure, and smart. As we move toward billions of connected devices, robust and secure firmware will be more important than ever. Or said in another way, secure firmware will be one of the biggest challenges and opportunities in the IoT ecosystem. So hopefully that gave you guys a nice overview of firmware as it relates to IoT and some of the design challenges that comes with the selection of that. So I yield my time back to the chair.
Excellent. So now we're going to talk a little bit about power. So and when you're powering these devices, they could go anywhere. If they're up on a pole, you need to make sure you power them there, etc. So how do you power all these things? And what's available up there?
Yeah, so if firmware is really the hero of IoT, power is kind of like the cold water that gets thrown on everybody's IoT dreams, right? So it's the constraint that no one can get around, and it really needs to be considered up front. These top three things are really kind of where we started at Nottinghamsburg when we collaborate with clients to determine a good IoT approach. One is really to start with the user experience. Everybody can design an IoT device, but can they design a great IoT device? That's really the separation of skill, really. And so taking into account how it's going to be used, things like that. The power consumption targets, right? Everybody wants it to be real small, clean cell powered, with stream video. Okay, so there's some constraints that need to be applied, and some compromises that have to be met. The other thing is really the usage and provisioning strategies. That's something that kind of gets overlooked up front. But that's critical because whenever you're manufacturing an IoT device, you have to kind of set it up for the end client or maybe an end group of clients. And so in manufacturing, that's a very complex process. And so there's certain tricks like NFC, things like that, where you don't have to have a wide broadcasting range to set up things. You can do QR with video. There's a lot of different methods, but then also once it gets into the user's hands in let's say the home or in a building for the elevator example, how are they going to set that up very quickly and very easily? So there's ways to do that don't require power. There's some thought that can be done up front that'll make that more smoothly. So again, this slide is to advocate for power. So some of the pitfalls that we've seen through the hundreds of IoT designs that we've seen through our doors is that really insufficient collaboration with groups. So at NS we have different disciplines: mechanical engineering, industrial design, firmware, electrical hardware, prototyping, manufacturing, insights. All these groups work together from the beginning in order to arrive at a good solution. So that Venn diagram that's up there is really meant to show that, that there's some overlap between all these different perspectives that arrive at a good product. However, Venn diagram is a very simplistic first order model, right? So everybody's kind of weighted equal. Well, in reality, there's different priorities that kind of take place, but having all those perspectives represented is usually leads to good success. The other thing is forgetting about the user experience. Again, I'm going to really focus on that one. So there's lots of different users, developers, installers, and the end user. So the developer is not going to want to have a battery-powered circuit board, right? They're going to want to have a line-powered. Well, the user wants a battery-powered device, okay? But those are things that you can kind of design in, put some hooks in the circuit board so that that can be supported. The installer is not going to want to necessarily power the device as they're getting it set up. So again, those are all things to be considered. Inappropriate solutions. So we've all been the victim of this if you've done any kind of design work in your career, where there's, the next best PMIC or something is coming out and it solves all your problems, it has all the rails that you need, it has great thermal management, but it's not available for another year. So do not design it in, it's a bad idea. The other aspect is really underestimating consumption. So power consumption is a big deal that's been mentioned. And so breaking it up with atomic operations and duty cycle and things like that, that's basic understanding. But then there's all these things that are like unsolicited operations. So things that kind of come out without being queried, that they come into the device, you have to react on that consumes power. Those are the things that really do, like site surveys and things like that, give you really good insight so that it can be an accurate power estimation at the beginning. The other one is a backup plan and a migration path. So these are things that are often overlooked. So the mechanical team backs you up in the corner and they want to use a very small battery. It should be really good, right? Because you did all the calculations. Well, you know what? At the beginning, plan for a larger battery. It's just plan for that, just in case it's a backup. A migration path to a larger processor might consume more power, so you have to make sure you have some capacity available within your power system. Those are all good things to consider. The other thing is compromised quality of signal, QoS. So a lot of times, like in an elevator or an industrial application, your IoT device is near proximity to a noise-emitting thing. Okay, so like a pump or something, and all that noise can sometimes contribute into a compromised RF signal, which means you're not able to do very high efficiency modulation techniques. Now you're consuming more power. So those are all things that, like I said, a site survey can address. Not architecting for a sleep state. This is the next last one, I promise. So component selection is obviously very critical there, and power supply topology. So the follow-on to this is really, sourcing and problems with bad implementation. We see a lot of schematics at Nottinghamsburg, and I can tell the ones that are well thought through because power is the very first page after the architecture, okay? That's because they know that there's a lot of switch supplies, switched rails have to be considered, sourcing is a problem. It's a very good way to set up a topology so that naming conventions show what is powered when, and you avoid that risk of sourcing. The last one that's not on this slide that I haven't heard a whole lot of people address is certification. So compliance work is a massive effort, an IoT device that has to be considered up front. How many countries are you going to support? The other thing is if you implement a cellular device versus a Wi-Fi or Bluetooth, cellular is one of the few RF standards that require performance objectives to be met. That is not to be underestimated, especially if you're trying to design something very small form factor. So, John, appreciate it. Thanks.
So this one is supposed to say security on top. And so, again, we have people filling in for Galen Fisher, he's convalescing, he just got out of surgery, and there's a situation. So these guys are going to pick it up, and Glenn, you're going to do it from the component side, and Joe, you're going to do it from the system side.
Well, from the component side, one of the things I would recommend, if cybersecurity group back there in the right-hand corner from me, I expect knows this, do not try to roll your own. You can quickly convince yourself that you've got an unbreakable cryptographic system that is going to be perfectly fine and it's going to suit all your needs. And I can almost guarantee you, it's not 100%, but it's 99.99 something percent chances somebody else has already thought of it and it's not secure. I can almost guarantee you that. It's very, very hard to build a good and strong cryptographic system. And that's why earlier speaker in one of the other panels talked about FIPS compliance and some of the other things. I've been through that. I've been involved in that. I've been involved in design of cryptographically strong algorithms as well as hardware, and it is not trivial. Hire an expert. Don't try to do it yourself. So I'll leave it to Joe then to continue from there.
Okay, excuse me, that was loud. When you're considering security in an IoT space, one of the things to think about is firmware updates. It's no small thing to put a device in a customer, a business, a consumer's physical space that could be compromised. And that's really important that you design that ability to update that firmware or that hardware in a secure way. One of the things that I'll talk about in the next slide is there are a lot of tools out there. Don't roll your own, don't try to figure it out, don't say, hey, I'm really clever, I came up with a really great way of updating firmware on 10,000 devices securely. You probably haven't, but a lot of really smart people have. Take advantage of those things. When you are going to update firmware, consider making sure the devices can validate that the firmware that they're loading hasn't been compromised in some way. There's no man in the middle. Certificates, encryption, signing is valid. But the other thing to consider is, are those devices booting the firmware that they should? And those devices, if capable, should have some sort of secure boot functionality in place as well. And the other thing to think about is all of these devices are collecting data and they're sending the data somewhere. The data should be secure in transmit, at least part of it. For example, if you have a Wi-Fi connection, that Wi-Fi connection should be secure. You want to consider whether or not you want to add extra encryption to your data depending on your use case. If you have a Bluetooth device that's talking to something else, is that connection secure? What kind of security do you need for your use case? And then once the data is in your data center, there's a whole lot of security you need to consider on that side as well. Not only from personnel, but encryption at rest, backups, where are you putting your data? If you're sending your data to a data team to do analytics, is that data secure? Do they have a place to put that where they're not potentially compromising that? There's a lot of security considerations to make, not only in the hardware and the ability to update the hardware, but also in the data center with the data that you have in your possession and what you're doing with that data as well.
I might add to that. One of the things, of course, to consider when you're creating a device that is going to be in the field collecting data, whether it's in the elevator example or a device that I'm wearing on my wrist, is the amount of compute power you have availability. And again, somebody on an earlier panel mentioned lightweight, and you need probably authentication, you need attestation, you need to know provenance of what your data source is, and there are lots and lots of concerns. So I would stress that getting somebody who knows something about it and who's been trained in it and who's gone through understanding what all of those terms mean and how to implement them in an efficient way that doesn't chew up a lot of battery, that doesn't chew up a lot of compute power, but still allows you to have that attestation, and allows you to have that provenance of data, and the security. And then sometimes there are some things that you may not need to secure. You don't have to secure everything, and you do need to consider what information needs secured and where, and whether it's at rest or in transit.